So the next topic we are going to get into is the history of the Earth. The idea that we learned in astronomy that the Earth is 4.6 billion years old. Now, as a geologist, it's going to be part of their job to kind of explain what has happened in our vast 4.6 billion year history, but also to kind of talk about the theory that the Earth is actually that old. There's a lot of different theories that you hear from other groups and what have you that say that the Earth is not as old as that. But science will use a lot of great evidence to kind of back up their theory that the Earth is in fact 4.6 billion years old. Now, what does that 4.6 mean? How does an object in space that's just a clump of dust and gas go through 4.6 billion years of history to form what we have today in the form of landforms or life, biosphere, waterways, atmosphere, all of that stuff. So geologists will map and chart that much time. Now, how are they going to know about it? Well, that's the next slide. How do they know is because of rocks and fossils are the evidence. So in this presentation, what I'm going to kind of take you down is a couple of different routes. One route is going to be one that I'm just going to mention and then walk away from, because there's a way to actually find out how old rocks and fossils are, their exact age, and that process is called absolute dating. The problem with absolute dating is the fact that it takes a high-level understanding of chemistry in order to understand the way to accurately give the age of rocks. So, for example, like you need to know about uranium-238 and radioactive decay and half-life. These are a lot of higher-level chemistry concepts that even as an 8th grader I know you don't need. Even as a senior in high school, I know they're not covering that intense into absolute dating. So obviously as a college idea, I don't want to get too far into it. What you will do as my amateur geologist is you're going to get into more of the idea of the relative dating process, where you're not exactly finding the exact age of these rocks, but what you are doing is getting an idea of how old they are compared to the other rocks in those layers. Same thing with fossils. We'll do an activity with fossils later on that will basically do the same thing. We're going to try and figure out the date relatively, but not necessarily the exact date, which would be absolute. So we're going to focus on the relative dating side. So in relative dating, there is one law that is usually understood and accepted, and for your glossary, I made sure that we covered it. It's the law of superposition. Now, in the law of superposition, as it says on the screen here, younger rocks lie above older rocks in undisturbed sequences. So I have a video clip that will kind of explain that in a little greater detail. Based on this picture, though, looking at this picture, you see that the Kaibab limestone is at the top of this picture, and then you see the Supai group at the bottom of this picture. Okay, so Kaibab limestone is here, and Supai is down here. All right. The Kaibab limestone is younger than all the other formations that are underneath it because it formed last, technically, according to the law of superposition. So younger rocks lie above older rocks in undisturbed sequences. The reason why I underlined in undisturbed sequences, because we know that the Earth inside has a lot of heat, a lot of pressure, and that can cause very disturbing sequences, and it can sometimes make relative dating difficult, and it kind of makes our superposition idea obsolete. So we're going to talk about what the disturbing forces are. So here I am in my son's room, because it's the only place in the house right now that I can videotape this next video. So what I want to show you, though, is the idea of the layering effect of the Earth. So in astronomy, we learned that when the Earth came together, we talked about we didn't talk about the Big Bang. We talked about a nebula collapsing on a cloud and dust and gas started to collide into each other. So I'm going to take Play-Doh here. Let's go with this color. Let's go with yellow. So gravity is this huge force that's in our solar system that started to bring these pieces of dust and gas together. I'm going to use Play-Doh as my example of the dust and the gas. So these are pieces of dust and gas that are, floating around in space, and gravity starts to bring these together. And when they start to bring them together, they start to collide. Okay? And when they collide, remember, this is a spinning nebula.
So when they collided, this orb, started to get larger. And then the orb started to get larger with more dust and gas as it started to collide. Now over time, what I'm going to use is different colors of Play-Doh to give you the idea of the fact that over time, this didn't happen real quick. There was a lot of dust and gas that was collecting over millions of years. So the orange is going to come on as another clump and it's going to run into this clob of the Earth because gravity's pulling it all together from the central source. And again, it's starting to spin together and starting to mix together. And then I'll grab another piece of, cosmic dust and gas and let it come in and collide with our glob. And notice how our glob, which started out small, is getting bigger and bigger as more and more things start to collide with it. So over time again, time has passed, and another type of dust and gas has come in and started to glob together and started to kind of layer up with the other layers. Now again, spinning nebula. That spinning nebula is kind of keeping this orb into that spherical shape. That spinning, that constant spinning, is keeping this thing into kind of an orbic shape. So again, over time, more starts coming together, and more starts coming together. And I'll even throw in some black to show later years of the dust and gas starting to collide together. When they collide together with that gravity source, they start to clump together. And again, it's spinning nebula, so it's causing this spherical shape to form. Okay. Eventually, over time, with all this motion of dust and gas collecting and the fact that it's spinning and causing that sphere, over time we get an orb the size of the Earth, which I'm going to use as my example here. This is going to be the size of the Earth. So technically, if you think about the Earth started as a central unit. That's where gravity was coming from, was bringing all those pieces together. And then from there, started to bring pieces on top of it. And those pieces on top of it started to layer on top of the other layers, okay, on our spinning orb here. So what you could say in the thought, or where the law of superposition comes into play, is the idea that the youngest layers are the ones on top, and the oldest layers are the ones that are inside the Earth, or the ones that are lower down, closer to the core. And the basis of that is back to astronomy. When the clump started to come together at the source of gravity, which is the center, that's where the first pieces started to form, at the core, and slowly by slowly started to work their way up to the outer layers, to what I have here. So what I'm going to do is I'm going to kind of cut this in half, my little child knife, because I'd hate to cut myself. I cut this in half, which you're not seeing me cut, but that's okay. So as I cut this in, you start to see the layering effect. Okay, and if I really had to, you see the core being that kind of orange color. So that's this core, this is the outer layer, and then you got the mantle and you got the crust. Okay, but technically the Earth is one large sedimentary rock, because the youngest layers are going to be the ones that are surrounded on the top. The oldest layers are going to be the ones that formed first. So the law of superposition is stating that the younger layers are on top and the older layers on the bottom in undisturbed sequences. But keep in mind, with all this collision and all this creation of this globe, when these pieces collided together, when these small pieces started to collide together and collide with other big pieces and big pieces and big pieces, what actually happened was the fact that we had they released kinetic energy. When they collide together, they release kinetic energy. That energy gets trapped in the center, and it's slowly trying to make its way to the outside of our Earth. Okay, so the center is a solid iron, which is denser than any of the other metals that were in our crust. That's why we have the solid iron core. But as it moves up, as heat moves up, this yellow section here, this outer part of the core, is the outer core. It's actually liquid iron, because it's, again, iron being the densest, it's sank closest to the gravity. And then you have the other rock layers. So we have heat inside there. Not only do you have heat from layer to layer, since the layering effect, the top layer is pulling down on the bottom layer, so you get pressure too. That's what gives us a lot of our metamorphic rocks. And it can cause rocks to melt, creating some of our igneous rocks. So that's kind of just a little video showing you how our Earth is one big sedimentary rock created in layers, and the idea that the youngest layers, the ones on the top, and the oldest layers are the ones inside the center.
So if the process of relative dating was actually easy, then we wouldn't have any disturbing forces that would cause the dating of these rocks to be any difficult. However, there are a bunch of disturbing forces, and the way geologists will figure this out is by comparing what's called geologic columns. Now, there's an activity with index fossils I'm going to do later in the week, or after this video, that will kind of give you the idea of the geologic column and how columns can shift and move. And you'll see that in one of the disturbing forces, that columns of rocks will shift and move and sometimes go out of alignment. There's a lot of different forces that can create that can cause that to happen. So that's one of the many disturbing forces that can actually make relative dating very difficult. So let's talk about each of those disturbing forces. So in your journal, I want you to do a couple things. I want you to describe the disturbing force, but I also want you to draw yourself a picture of the disturbing force. The first one on the screen is the fault. And fault lines are areas where earthquakes take place. Fault basically means break in a rock. So when you look at this picture here, I'm going to use we'll go with red. This line right here is the fault line of this rock, which means this rock broke in half, or this huge rock section broke in half at some point. Now, the arrows I have there are kind of a speculation to the idea that forces had to have separated these rocks and pushed them in opposite directions to each other, and my evidence to that is the fact that I've got a rock layer that's black here. It stops at the fault line and then continues up here. So how I know they match up is because I've got all this white stone that's similar to the white stone that's up here. So at some point, rock layers don't form independently to each other in different areas. They're all going to form at the same time in the same location, and they're going to be as straight and flat as they possibly can because gravity will make them that way. So not only is this rock section tilted, but it's also separated, the fact that one rock layer is much higher. So I speculate with these arrows, I say that maybe there's a force that pushed this one up while pushing that one down. So this is a fault line. This is a way to that makes relatively dating the rocks a little difficult. So now geologic time happens very slowly. There are such things as catastrophes, volcanic eruptions where lava pours on the surface, earthquakes that happen in a matter of seconds and can last for a couple minutes. Absolutely, and that can cause changes to the Earth's surface. Most geologic change, however, takes a very, very long time. So for the rock layers to separate themselves as much as they did in this picture, it probably took hundreds, if not thousands of years, way beyond our generation, way beyond our lifetime. So what we're looking at is an aftermath that could have happened, I don't know, 10,000 years ago. That they started to push and slide, and there was an uplift from the ground that pushed the one side up, or maybe sediment that was so heavy that pushed the other side down. I don't know. But we do know that this does make the dating process tough. Unless I take the absolute date of these rocks, I don't have a clear answer. Another disturbed rock layer is going to be the intrusion rock layer. Now, in igneous rocks, we talked about it, igneous rock becomes a brand new rock when it melts and freezes, which means melts and rehardens. So no matter what the rock was before, if it melts and hardens, it automatically becomes an igneous rock. Well, imagine that inside the Earth. When you've got all that heat and pressure building inside the Earth, it will wear away and melt away existing rock layers. I said the Earth is one big sedimentary rock. The magma that's inside the Earth will actually create but it will destroy the existing rock layers and melt them away. So that the point where you're looking at this magma chamber, which stretches, red's the wrong color for that, when it stretches like right up in here and these existing rock layers, that magma chamber pretty much is now, when that hardens, it's going to become brand new rock. So how are you supposed to tell what's new, what's old, relatively speaking? Technically, the bottom layer, this layer here, this magma chamber that's now igneous rock, is technically the newest rock. It's the youngest rock. And that totally goes against our law of superposition. Not only that, is if I was going to take the law of superposition, this layer that I'm coloring in right now is the oldest layer, and then this layer is the youngest layer. They're right next to each other. That makes that very difficult. So intrusion is another one of those disturbing rock layers that can cause a problem when trying to figure out the age of rocks. This is my favorite picture. What you have here is rock layers that are not sitting straight up and down. They're sitting in a kind of a rainbow shape. Okay, so much so that this, to put it into perspective, these are people standing at the bottom of a mountain, or the mountainside, and looking up at the U-shaped rocks. These rocks went through so much force that they bent and they buckled, and instead of being straight lines across, they got pretty much compressed into those U-shaped rock layers. This process is called folding. When you've got those types of processes that are so dynamic, that they're so big and massive, that it can actually take rock and bend it and buckle it as much as it does on such a large scale, that really says a lot to the internal forces inside the Earth that can cause that to happen. If you've got rock that's folding, that is another way that this can be very difficult to age the rock. So yes, for this picture, that's probably the youngest. Down here is probably the oldest. Yeah, I get that. But what happens if these guys fold together and let's say it tilts over? Let's say it moves over. Let's say the right side of the mountain, these layers are going this way, but you've got older and younger close to each other. It makes the process very difficult, is what I'm kind of leading towards. The last way a rock layer can be disturbed is if the rock layers get tilted in some way. Now the tilting can happen from uplift on one side or maybe a downshift on the other side, where forces can push rock layers downward and tilt up the existing layers, or maybe the uplift from inside the other internal forces can push rock layers upward. But the result is seeing strata, the layers of rock, in kind of a diagonal pattern. So looking at the picture here, they look like they're going that way. They're slanted. So tilting is another one of those disturbing rock forces, or disturbing forces that disturb the superposition of rocks, and it might be tough to get their age. Now, looking at this picture, again, just kind of a snapshot, I would say youngest and oldest would be down here, but do you absolutely know that for sure, unless you absolutely date those rocks? So the relative dating process can be very tricky. You just got to be careful that there's no other existing conditions that might make your work wrong. So for this next part, I have a couple of pictures for you, and what we're going to do with these pictures is we're going to actually try to relatively date these layers of rock. We're going to start with figure A because it's an easier picture to kind of go through. Now, just to kind of give you a heads up, I gave this worksheet in class, so I know the bricks here are limestone, and I'll erase this in a second so it's easier. I know this is granite. Excuse my sloppy writing. I know this is sandstone. Well, that's it for this one. And then if we get to it over here, when we get to figure B, this is going to be shale. Each of these are sedimentary rocks except for granite. Granite is an igneous rock. So that'll become important to remember as we talk about the age of these rocks. So what you need to do is you actually need to try to organize these rocks into, or at least age, relatively date these rocks, oldest to youngest. So where you think, and again you may have to pause this video to do it, where you think their oldest rock is, you're going to put, based on the law of superposition, but at the same time with some disturbing forces, put an A where what you think, let's try that again, put an A where you think the oldest layer is. Okay, so I gave you a little think time there. Now, you might have put it here, or you might have put it here. You had a couple of choices there. I would say that the oldest layer is this shale that's down here. I didn't see this the first time I was matching them out. Okay, here's why I say that. This is granite. All of this is granite. Okay, granite is an igneous rock. As you can see, there were existing rock layers that were there before, and this igneous has kind of melted its way through the existing rock layers. So sandstone and limestone and even shale was destroyed and turned into granite, was turned into igneous rock. So I would say the oldest rock layer is going to be the existing rock layer that was not affected by the igneous intrusion, and that's going to be the shale that's at letter A. Then I'm going to keep going and say that this is B, the sandstone. This layer of limestone is C. This layer of sandstone is D. This is, which is near the surface, bedrock, is going to be E, and then the granite is actually going to be F, meaning that A is the youngest and A is the oldest and F is the youngest. So for figure A, this is probably how we're going to relatively date the rocks, because again, the intrusion would have come later. Those layers had to have existed there before the intrusion came up and melted them away. Now, what also this picture offers is a fault line. So we have an intrusion and we have a fault. So we have uplift, it looks like. It looks like it got pushed upward. and we're getting a rock cliff that's made mostly of limestone over here, and we have a higher, area. So that kind of gives us the idea that this was an uplift sometime in the course of history, and the fact that the two layers don't match up, and they actually match up higher up, kind of gives you some clue to that. Okay, now the other side of this is figure B. Now with figure B, there's a lot more going on. You've got sandstone, you've got shale, limestone, sandstone, limestone, shale, and more sandstone. You've got intrusion, you have an intrusion up here, and you also have a fault here as well. Now, take a look at this. Hang on, let me erase this. Take a look at this. The intrusion had to have happened before the fault took place. And look at the fault line too. It adjusts itself to the point where it stops. The sandstone layered itself on top of the existing ground. This is a lot tougher to kind of age. But I would say if you're going to go youngest, and honestly, I'd even go younger than that because you see another intrusion over here. This over here is going to be your youngest part. This is going to be the event that happened last. An intrusion almost looks like an intrusion that came up through the sandstone and almost made a volcano on the surface. It's now hardened granite, so it's not, it's not active anymore. But the fact that you've got a granite slab over here within the existing sandstone, this is giving me the idea that this is the youngest piece of this. Now, oldest, again, I'm going to go through my layers, and I would say, if I'm going to put an A on the oldest of anything, it's going to be that sandstone that's at the bottom there. And I start working my way up. B, C, D, E here. Okay. And I would go F to there. Just because that fault line, this had to have existed before that fault line existed. And the fault line comes after the intrusion. So honestly, my next letter would go here. This is G. And then this is H, because this sits on top of all that going on. This is just a connection of it. And then, so your youngest layer is actually layer I in this case. Based on what we talked about with all the disruptions and all the law of superposition, that is how I would age figure B. So how well did you do? Hopefully you figured that out. So in looking at this, I know I've talked about unconformities with other classes before. I'm going to skip unconformities. So this video is just going to kind of just fast forward through these slides about how rock layers can sometimes go missing, and those missing layers we call unconformities. Well, I don't think you need that right now. So I'm just kind of skipping through, just quickly flashing through each of the slides, so I can get to geologic time. Now, also to kind of finish this up, remember I talked about absolute dating. Absolute dating gets you the exact ages of rock, where relative dating only gets you an approximation to the ages of rocks and fossils. Absolute dating is a process, as you see, establishing the age of rock or fossil, and by determining the number of years that has existed. Well, that's pretty much figuring out its age. But again, the concept is such a higher level chemistry concept that I am not going to hit that with you at this time, and I don't think you need to know it for any type of test in the future. So finally, and I don't get this until like a second day of notes, finally we get into the idea of geologic time scale. How do you take 4.6 billion years and map it out in a timeline of sorts? So again, geologists have the huge task, I guess, to dating out 4.6 billion years of Earth's history. So what geologists are going to do, and as you're going to see on the next screen here, is they're going to break it up based on events. These are not going to be exact specific dates, like May 3rd or June 5th, because you're talking about 4.6 billion years, and the modern calendar is only about 2,000 years old. Actually, it's not even that old. It's a little less than that. It's about 14? Actually, no, Gregorian calendar is 1400, so it's only about 6 or 7. Our modern calendar we use is only about 600 or 700 years old, so not very old at all. Anyway, so geologic time is not going to be an exact specific date, but it's going to tell you a span of years. So they're going to break up the time scale into 4 distinct time periods: the eon, the era, the period, and the epoch. So we will discuss them on the next slide. So here is a picture, and I could probably make it bigger for you. Here is a picture of geologic timescale. You'll notice that the largest chunks of time on the left here are the eons, and there are 4 of the eons. You got the Hadean eon, you got the Archean eon. Well, that doesn't work, does it? So you got Hadean, you got Archean, you got Proterozoic eon, and then you got the Phanerozoic eon. We live in the Phanerozoic eon. Okay, and what breaks these eons up is pretty much development of the Earth. You know, the Earth forming its rock first, and then maybe the atmosphere came next, and from there maybe the water on the surface. With all 3 of those events and those eons passing, you can see the spans of time. It takes over billions of years for those eons to develop. To get to the Phanerozoic eon is when life appears on the Earth. So that's why this eon is our current eon, because life still exists on the Earth. So life only goes back about 540 million years on the Earth, not all 4.6 billion. So as you look at this chart, it kind of breaks down each eon into smaller sections called eras, and our current eon has 3 eras: Cenozoic, Mesozoic, Paleozoic. We are in the Cenozoic era. Each era is broken up into periods: quaternary, tertiary for the one we're in, and then the others down there. We're currently in the quaternary. And then each period is broken into smaller sections called epochs. So we are in the Holocene epoch, of the quaternary period, of the Cenozoic era, of the Phanerozoic eon. And as you see how long we've been in this era, it looks like about 10,000 years we've been in this epoch. And then we've been in this era for about 65 million years. And that 65 million is going to become actually a very noteworthy number in just a second, as I talk about each of the eras. Remember, each of the eras is going to dictate in this eon the type of life that existed during that era, and which of the type of life was the more dominant species. So that's what we're going to talk about on the next slide. So just as a review, the scale is divided into eons. That's the big chunk. Eras are, break up the eon into eras. Each era is broken into periods, and each period is broken into epochs. So eons are the largest span of time, epochs are the smallest. So let's talk about the 3 eras on the next 3 slides. In this eon, the Paleozoic era, which is the one that lasted for that was about 540 million years ago to about 248 million years ago. A small chunk of change there, huh? So this was when life started to appear on the Earth. That's why they break this eon into kind of the life eon, or existence eon. It means old life, and at the beginning there was no land organisms. Most life, if it was plant life, started on the surface, but most life that was animal-based, or bacteria or protozoa, was in water. And water is the necessity of life. Oxygen became a necessity of life for a lot of things. So at the beginning there were no land organisms. Over time, organisms evolved to the point where they were water organisms to the land organisms, and then from there evolution kept going. In the middle of this era, plants started to appear, and then by the end, amphibians and insects are the most abundant species during this era. Well, that brings on the Mesozoic era, which is the age of the dinosaurs, which is the middle life era. And this lasts about 248 million years to about 65 million years ago. This is the age of the reptiles. The reptiles were the most dominant species. Dinosaurs are reptiles. So birds and small mammals will begin to appear. Now, dinosaurs and humans did not exist at the same time, because they're actually 2 different eras of time. We are the dominant species, or mammals, to be specific, are the most dominant species of our current era. At this time, the reptiles were. Which leaves us to our current era, which is the Cenozoic era, which means recent life. And it's been going on for like as you see, 65 million years. Age of the mammals. We're the most dominant species because we are. It is what it is. Mammals are the most dominant species. And again, a lot of the animals from the beginning of this era are now extinct, like the woolly mammoth, the saber-toothed cat. I know everybody always brings up the idea of Ice Age, and the idea that dinosaurs and humans lived at the same time. They did not. Okay, so that's what makes a cartoon and not always realistic. But some of the science that's backing up, like plate tectonics and continental drift and all this stuff, there's some accuracy to the scientific settings of these cartoons, but reality is, no, mammals and dinosaurs really didn't live at the same time. If they did, it was at the end of that era. Now, what ended the dinosaur era and turned it into the human era? The theory is a huge celestial object from space fell down and crashed into the Earth and pretty much created a chain reaction of events that pretty much killed off the most dominant species on the planet and allowed for other species to take over, pretty much. When is our era going to end? When's this era going to end? When this human species does not exist anymore, and by that point, nobody's cataloging that. So hopefully our era lasts for a long time beyond the 10,000 years it's already lasted. So that's kind of a conclusion of geologic time. I just want to do a brief overview of geologic time as it came to the history of the Earth. So in the coming days, we'll have a quiz that goes along with this, and then we get into plate tectonics, earthquakes, volcanoes, which is the end of the geology unit.